So my talk today is is a joint work with Mathieu Dolbeau, who has graduated last year, who got his PhD last year from Paris 6 in Paris, with Albert Cohen, who also was my PhD advisor back in 2014, and I believe he's now in Aachen too. So this work is on sampling for least square, and we propose a method for what we call optimal sampling, meaning that given a polynomial space, given a projection space of dimension n, we will only have to sample like a linear, a multiplicative linear sized sample in n to get the same accuracy and stability result that were obtained before by co-authors like Raoul, Albert Cohen, Giovanni Migliorati, and others. Okay, so it's the same talk I gave in UQ 2024, a month ago, with few changes. Please feel free to stop me if you have question or if you need references. I have few references on the slide, but feel free to contact me if you need more references on the subject. So the structure of my talk is the following. First, I start with the classical motivation, let's say, and then I'll details i.i.d sampling for weighted least square, and then what I called adaptive sampling, which is the idea we have in our paper, and then I'll finish with some numerical experiment and perspectives. So the main motivation is function approximation. So we have a function. I'll call it throughout the talk f. So f belongs to some space V, and we would like to approximate the function f. In our settings, like in my PhD or also the work co-authored with Raoul, the f is the solution of subparametric PDE. So there is a PDE, there is an underlying differential operator, and the PDE is parametric, which means the geometry of the domain or some diffusion coefficient or some other coefficient is parametric, depend on some parameter. In the other paper, we use the notation y in some parameter y. So f of y is itself a solution of some PDE with fixed parameters. So for every parameter y fixed, f of y, which belongs to, let's say, h10, is the solution of some PDE. Here, I'll just use x, and x as a generic notation for a variable. So here, I won't be talking about parametric PDE. So u can be highly dimensional. So u can be the hypercube in dimension D, or can be any other domain. And v, let's say, just some Hilbert space. Okay, so as I said, the objective is to approximation the function f, and we will approximation with some f tilde from a low dimensional space, and ideally in the uniform norm. So everywhere in the domain U, we would like to approximate to f, or in average, in least square average. So for this, there's a plethora of method. There is sparse grid, interpolation, least square, all other kind of projection operator. So there's a lot of method. This talk, I'll just talk about the least square, and more specifically, weighted least square. So for least square, the setting is the following. We have an approximation space. So the low dimensional space I was talking about here is an approximation space, which is spanned by some basis. Our denote phi1 to phi(n), and we'll query f at point of the domain U. I will call them throughout the presentation x1 to xm, and then compute a weighted least square approximation f tilde to f, which is a solution to this minimization problem. So we minimize this quantity over here. So for example, in machine learning, neural network, etc., this is what is called ERM, I think, empirical risk minimization. So we just minimize the difference between f and f tilde in the least square, in the empirical least square sense. So typically in approximation theory, we are interested in quasi-optimal convergence result, the quasi-optimal conversion result rate. So we would like, for example, to have a procedure, an algorithm that produce an f tilde, which means will select the query point and will select the weight Si in a way that in average the convergence in the least square sense is quasi-optimal compared to the best conversions in the least square sense. We can also be interested in convergence almost surely. For example, here, this is also kind of result that is usually given in the least square paper, which is comparing the convergence in the least square sense using the best approximations, the best approximation in the uniform sense. And we can also be interested, like in interpolation of sparsification, to obtain a convergence in the uniform sense compared to the best conversion in the uniform sense, with here not a constant, but what we call a Lebesgue constant. Actually, it can be, there are a few examples, like in one dimension, if you use how it's called, Laval-Poussin operators, you can get here a constant. But in general, it's not a constant. In general, it will be a Lebesgue constant, which means it will depend on the space Vn or in the dimension n of the space Vn. So just for later, let me use introduce this notation. So I'll call the best approximation in the least square sense En of f, and the best approximation in the uniform sense, assuming, of course, that Vn is included, the function in Vn are all bounded. We'll call it Enf with the infinity as a prefix. So, given any, as I said before, the phi1 through phi(n) was the basis of Vn. So given any basis, given any basis of Vn, we can compute f tilde using. I mean, we can have a closed form for f tilde using what is called the normal equation. So it's simple. We will look for C1 through Cn, which are the coefficient of f tilde in the basis phi1 in the basis phi. So the vector, now if we now go to linear algebra, the vector C, sorry, is the solution of what is the so-called normal equation, G C equal to B, where G is just the empirical inner product between the elements of the basis, and B is the empirical inner product between the elements of the basis and the target function f, and the empirical inner product is defined here. So here I'm using the notation for complex number, but we can think of it just real number without the overline. So if G is non-singular, so we have a C, and that's give us the coefficient of the function f tilde in the basis phi. And usually that's not what we do. Usually we have a minimization problem, and we'll solve it using, for example, gradient descent or stochastic gradient descent. But here I just wanted to introduce the Gramian matrix, and we'll see later how the Gramian matrix is related to the stability and accuracy of weighted least square. So let me just note that this Gramian matrix is a sum of rank 1 matrices. We can write it as a sum of rank 1 matrices just by developing here the empirical inner product. So we can write it as a sum of the weights Sk, column vector Vk, column vector Vk star and row vector Vk. Yes, where Vk is just the basis phi applied to the point of the sample x case. Okay, so we have a sample of size m. We have a polynomial. We have a space of size of dimension n. And what we will see now is how big can m be, and how to choose the sample and the weights, so we can get decent approximation results using weighted least square. So the first is the most straightforward idea is to use random sampling. So from some probability measure, and I'll detail here random sampling, and I'll show you at the end how the weights are chosen. So the most straightforward sampling is the sampling according to the same measure d mu. Let me remind you that the space L2 that I defined, the underlying measure is mu. We can also sample according to some discrete measure, which means we have a lot of points. I will just pick some point of this point, like in a uniform manner or in some other manner. We can also sample according to some equilibrium measure. This is related to the domain U and the space Vn. We can also sample according to the Christoffel measure, which is related to this, of course, the space Vn through the basis phi. Here, the basis phi is orthonormal. In the slide before, it was any basis. It was an arbitrary basis. But here, if we have an orthonormal basis, what we call a Christoffel measure is this measure over here. And we can also choose to, there are a lot of other random sampling technique we can choose from. So let me show you. I mean, this is like an algorithm, but it's just a loop. I wanted to put it here so I can compare it to the two algorithms I will propose later. So we start with the zero matrix of dimension n times n, and we will every time we will draw a point xi from the underlying probability measure from here. We'll choose the weight, which will always be 1 over the density of the measure with respect to mu, and we enrich the matrix AI as with the rank 1 update matrices, so that at the end we obtain the sample, the weight, and the gray mean matrix G. I'll call it G from now on, which is the matrix AM. So this is i.i.d sampling from a measure that has a density with respect to the measure mu. So I'll start by giving theorems regarding this type of sampling, and later I'll introduce our results. So first, by the accuracy and stability results for i.i.d sampling are obtained through the study of the concentration of the matrix G. So actually, how well conditioned the matrix G is it around the identity matrix. So here I'll assume from now on I'll always assume that phi is orthonormal with respect to mu, so that given an element f in the space Vn, the L2 norm squared is just the Euclidean norm of A squared. And now if I define, or I have already defined the semi-definite inner product related to the sample and the weights. And with using this semi-definite inner product, we know that the empirical norm squared formula is A star GA, or A transpose if we're just working with real valued vectors. And as I said, we would like to understand how a condition G is around the identity matrix. So here, the underlying norm here is the spectral norm. So I know that if the spectral norm of J minus the identity is larger than some small number delta, which is a number which is between 0 and 1. So if we would like G to be non-singular, this is equivalent to the existence of A, such that such that this quantity over here is larger than delta norm of A squared, which is also equivalent to the existence of some element in V. This is a Vn, and here is a M. So there's the existence of some element in Vn, so that the difference between the empirical norm and the real norm is larger than delta, the real norm. In other words, if we would having G well conditioned around the identity matrix is equivalent to having an equivalence inequality between the real norm the real norm in the L2 space and the empirical norm, which we have defined here. Sorry, this is an N here, and this is an M. This is an M here, and here it's an N. So as I said, this is an equivalence result. Having well conditioning is equivalent to having equivalence between the empirical norm and the real norm. How can we have that in the context of i.i.d sampling? So this is it's actually we can quantify how the random matrix G deviates from the identity matrix using matrix concentration inequality. So let me just define first the This is actually a supremum of a Christoffel function, but with the underlying, with the measure, with respect to the measure W d mu. Once we have this, we know we can quantify how the matrix deviates from the identity matrix. And as I said, this is obtained by classical argument from matrix concentration inequalities. So this theorem first appeared in a paper by Cohen, Davenport, and Leviathan in 2013. And it's based, as I said, on inequalities that predate the paper. For example, the paper by Prof from 2012, or some other paper regarding matrix inequality, symmetric or Hermitian matrices concentration inequalities. And this result also is I think it is also approved in the recent paper by Cohen and Migliorati from 2017. So up to this point, this result is simply regarding the conditional of the matrix G. But actually, it can be also this. It has also implication on the stability on an accuracy of the least square scheme, of the weighted least square scheme. So let me just simplify the notation. I'll take here delta equal to 1/2. So if I apply the theorem as it is, and I would like to matrix to be well conditioned around the identity matrix up to 1/2 in terms of the spectral norm, I get this result. As soon as M, which is the sample size, is related to N using this inequality over here. So kappa is just a constant, it's just a number. M over log M larger than some quantity in N actually is equivalent. Let's say it's equivalent to M being larger than this quantity over here up to a logarithmic factor in N. Okay. So for example, if this quantity over here is the best quantity we can get, which is N, we up to have the sample size related to N equal to N log N times some constant, we can have well conditional of the Gramian matrix. So for the next slide, let me just define this quantity over here, which is sorry, here there is an M here, which will appear in convergence rates. So again, as I said, the well conditional of the matrix G has implication on accuracy and stability of the weighted least square scheme. And the approximation results I'm giving here can be found in the same paper by Cohen, Davenport, Leviathan, or the paper by Cohen and Migliorati, or also my paper with Cohen and Raoul, Nobili, and Migliorati. There are differences, but the idea is the same. Up to have well conditioning, we can get good approximation result here. To keep the slide and the presentation simple, I'm just giving you the noiseless case. In the case of noise, similar convergence rates are obtained, except that you need to balance the errors here with the noise. So the first result is using weighted least square, but truncated with weighted least square. So the idea here is the function f is also uniformly bounded. So what we call weighted least square, just to compute what I call truncated weighted least square estimator is weighted least square estimated that I have denoted f tilde and then truncated using the norm v of f tilde and truncate to some constant tau. So the result here, if we sample the point x1 to xn using i.i.d sampling, and we use the prescribed weight Si, and then we solve the weighted least square problem, we obtained a weighted least square estimator that satisfy in average least square sense almost a quasi-optimal convergence because this converges to zero as m goes to infinity, or we can just see it as a constant, up to a plus a term that is related to the L infinity norm of the function. Here it's f not u. A similar result if we use condition weighted least square. By condition weighted least square, we mean we sample, we get the matrix G if the spectral norm of G is larger than 1/2, because these results are in the case delta is equal to 1/2. If spectral norm of G is larger than 1/2, then we solve the least square problem. If not, we start over. So the convergence rate we get is the following. So it's actually similar to this one. And there's also convergence in the uniform sense. So if U is also bounded, so we have a convergence not in the average sense, but in overwhelming probability sense, let's say. The non-truncated weighted least square estimator we don't truncate can give us this convergence rate. Where here, let me remind that here is it's the L2 norm. It's not the L infinity norm. Here is the L2 norm, and here is the L infinity, the best approximation in the uniform sense. Actually, in our paper we have also a result, as I said, using which will involve the L infinity norm on the left too. So let me give you an example of the theory I presented so far in the case of polynomial. So this is from our paper with Raoul. So if we consider non-weighted least square, which means I choose W equal to 1, and I do non-weighted least square projection on spaces of polynomials. So the spaces of polynomial we used in this paper are what we call tensor product or tensorized polynomials with indices belonging to lower set. So I hope everyone knows what's a lower set, but a lower set is just simply a set of indices in n0 to the d, where once you have an index, any index that is does this index in component wise stay also in the set of indices. So for such space of polynomial, it can be shown that if we do weighted least square, actually this is not even related to least square. This is just deriving or upper bounding the quantities Kn for different type of probability measure. So if we use the uniform measure, we have a bounding of Qn, actually smaller than n squared. If we work with the tensor product arc-sign measure, we have a better bound. So n to log of 3 over log of 2. So I think it's something like 1.58. And there's also, I think Giovanni has a paper where for different families of measures, these are also tensor products of Jacobi measures. He has estimate of key of n. So in this setting, we know that, for example, if the sample size is n squared log of n, or if it's n something like n log 3 over log 2 log of n, up to some constant, of course, we have stability and we have accuracy of the weighted least square backed by the theorems I just presented in the last slide. I want also to have this slide over here because I will use this estimate because we use them in our paper when we apply our finding to the interpolation regime, meaning the sample size m is equal to the space dimension n. Okay. So this first part of my talk was more general on weighted least square. Now I have another half an hour. I'll quickly present our finding. So as you can guess, or from the plan, it's not i.i.d sampling. It's adaptive sampling, meaning it's history-dependent sampling. We will sample the point x1, x2 through xm, where each point xk will depend on the preceding point xk up to xk minus 1. Okay. So first, I'll introduce some notation, and then I'll give you the two algorithms we have in the paper. So again, phi is orthonormal. Given any matrix, this is a simple calculation. You can show that this integral is equal to trace of m. In particular, if m is Hermitian and positive, this will define a probability measure. And this actually, from this type of measure, we will sample. And let me note that the Christoffel measure is just a particular case of this type of measure where the matrix M is the identity matrix. And every measure here is dominated by the Christoffel measure up to some multiplicative constant, which can be at most equal to n lambda max of m over trace of n. Why am I reminding this? Because eventually, at the end, what we do in our paper is sampling from the Christoffel measure, but then deciding to accept or reject a sample depending on some criterion at iteration k. So this is the first algorithm. It has this exact same structure as the i.i.d algorithm, except that when we sample from this type of measure that I presented in the previous slide. The weights are the same, let's say, as in the i.i.d sampling. Here we don't care this. Here, our sampling, actually, in our sampling, we don't care about having a well-conditioned and around the identity matrix. All we care about is having the lambda mean, the smallest eigenvalue of the gray mean matrix G larger than to some predefined constant. Okay, so it's the weight choice is not as the i.i.d algorithms. So in blue here are the same step as the algorithm, the plain algorithm, except there is some work before that I'll just read from here. We define a matrix. We define a matrix which is also Hermitian positive, and we define a barrier L of I, and every time we will push the barrier and then define another matrix, which will also be Hermitian definite positive. The matrix M from the previous slide is just Z of I plus a multiple of the identity matrix, and that's the matrix, which will define the measure which we will sample from. Okay, so basically, this is the idea of our algorithms. We use adaptive sampling in the sense in every iteration we sample from a probability measure that depend on a matrix that depend on the sample obtained up to iteration k. Okay, so I'll just give you properties that are easily verified and show that the algorithm is well defined, and then I'll give you the proof why this produce Gray matrices with strictly positive smallest eigenvalue. So as I already said, the matrix will always be positive definite. This is verified because actually the delta we use here will depend on the trace of YA. Another property is relating the matrix Y of A plus 1 and Z of I. Actually, these matrices are almost the same, except that the barrier is different. So we have a closed formula between the two, which there's a rank 1 update involved. So by Chairman Morrison formula, we have actually a closed formula between Y A of 1 and Z of I. The matrices Z of I and Y of I are just resolvent with respect to the matrix A. So they commute. So we have this property over here. So once we having all those properties, we can quantify the difference of the trace in the matrices Y, I. And how the algorithm is defined, how we pick the next, randomly the next point xi, we can show that in expectation, this quantity over here is smaller than 0. So if we apply expectation 1 more, we can show that the trace of these matrices are non-increasing in average. So why do we need this? Because if the traces of yi are small, which mean traces of this matrix is small, this prevent the smallest eigenvalue of this prevent the largest eigenvalue of y to be very big, which will prevent the smallest eigenvalue of a of I to be small, to be close to 0. So the main theorem in this fourth part is the following. So given a p, which is the probability, and given a ratio r equal to n plus 1 over n, the random matrix am, because it's also a random matrix, generated by algorithm 1 satisfy the following. So the probability that the smallest eigenvalue of the Gramian, this is the Gramian, to be larger than alpha, which has a closed formula related to all the input of the algorithms, is at least 1 over p. So the proof is the following. So by the monotonicity of I showed in the previous slide, we have this property over here. So we can sum up the traces, and we have by Markov inequality. This is where we use actually the fact that we are still using random sampling, although it's adaptive sampling, not i.i.d. sampling. So we use Markov inequality to derive this inequality over here. Then this inequality give us a result on the on the quantity over here, the 1 over the traces. And once we have this, we know actually, if I go back to the algorithms, we know that the barrier Lm of 1 is just equal to L0 plus the increment we were adding from one iteration to the other, which has this form over here. So this give us that Lm of 1 plus 1 is larger than alpha. And once we relate, since we know that the matrix Y n plus 1 is positive, we have L n plus 1 as an estimate, as an upper estimate of the smallest eigenvalue of the Gramian matrix J. So these results are related to the well conditioning, to the well condition of the matrix J. Now, the main result regarding approximation is the following. So if we sample according to these algorithms, having well chosen input parameter, which will be related to the ratio between m and n, we get a quasi optimal convergence result, except that there is a, if you look here, there's a power 7, so it's a quasi optimal result. But in the interpolation regime, when m is close to n, this constant can be overwhelming, can be quite large. And this result is obtained actually by optimizing all the parameter p, epsilon, and gamma, so that we get the best constant possible, and we get this constant here. Actually, it's not the best constant possible, but we know that we can get this constant over here by carefully choosing epsilon and gamma as these parameters. So this first result show that we can get quasi-optimal results. This was one of the objectives on the first slide, using linear size sample. Okay. So this was the first algorithm. This second algorithm is almost the same as the first algorithm, but it will give us better results and even result in an interpolation regime. So the structure of the algorithm is the same, except that at the sampling step, we sample from this odd-looking measure, which involved z square and z. And actually, this odd-looking measure we choose it on purpose because it will give us the result of I have on the following slide. So as far as the property of the algorithm are the same as the algorithm one, the algorithm is well defined. The matrices are all Hermitian positive, and we can sample from this measure. We can show that we can show that the total mass of this measure over here is larger than 0. So we can sample from this measure. So the algorithm is well defined. The main property why we choose the measure the way we choose it is the following: is that we don't even hope the traces to be non-increasing average. Actually, we will spend more time sampling, and we force the trace of yi to be equal to 1, the same as the trace of y0, or I think y1, of y1. Why is this? For the following reason. So the smallest eigenvalue of the gray mean matrix is equal to the barrier L of m plus the largest eigenvalue of y m plus 1, the inverse of the largest value of y m plus 1. We have a closed formula for the barrier Lm, because every time we were just adding a fixed increment, and we started in minus n, so it's equal to minus n plus m delta. And this is larger than the trace, the inverse of the trace, which is equal to 1. So at the end, we obtain that the smallest eigenvalue of the gray mean is larger than this quantity over here, which involve n and involve the other input of the algorithm. Actually, there is one input of the algorithm, is delta and kappa. Kappa is not showing here, but it will show in convergence rate. So this algorithm, using this algorithm, we have a way to force the gray mean matrix to have a smallest eigenvalue strictly larger than 0, and we're still using random sampling. So regarding this algorithm, we have the following theorem, which will give us a convergence rate in the average sense, in the least square average, in expectation sense, and also in the almost sure sense if we compare to convergence rate in the uniform sense. And here the powers are small. Actually, there is a power 2 here, and there is no power here. And let me just remind you, by conditional weighted least square, we mean we assemble the matrix J. If the smallest eigenvalue is larger than this quantity over here, we solve the least square problem. If not, we start over. So the conditional weighted least square, based on points selected by algorithm, do with these inputs, with well-chosen inputs, actually, with a well-chosen input, delta, give us this quasi-optimal convergence rate in expectation or in almost sure sense, and depending on how we choose delta. So, for example, if we want if we want a convergence, if we choose kappa is equal to 1/2, we get convergence. We get almost as good convergence in expectation sense and also in almost sure sense. But there is a free parameter kappa, which we can have equal to, for example, is equal to 0. Equal to 1 here. So we can push the convergence rate, or to get very good convergence rates in L infinity sense, which will allow us to get good results in the interpolation region. And so in the interpolation regime, m is equal to n, and we have this mismatch in the formula using the formula of the ratio. There's a mismatch between m and n, which we exploit here. So we have an estimate of this number over here, which show here. So we have a theorem in the interpolation regime using points selected by the algorithms. With this input over here, we get a convergence in the expectation sense, not quasi-optimal, but there is an n shown here, and similarly convergence almost sure if we relate to the best approximation in the NFT sense. So if we stick to this regime, to kappa equal to 1, actually combining the estimate over here with an inverse equality between the L infinity, the L2 and the L infinity, which always involve the Christoffel function or the maximum of the Christoffel function, we get the following result. So the interpolation, the least square estimator, or the interpolation estimate, the interpolation approximation, because m is equal to n, at the point selected by the algorithm with the input, achieve a convergence in the L infinity sense, which we can relate to the best convergence in the L infinity sense, in the uniform sense, up to some constant, a Lebesgue constant here, which is 2n square root of kn. What is kn? Is just the supremum of the orthonormal base, the squared sum of the orthonormal base. And since in interpolation, it doesn't matter how the points are selected, since in interpolation, we can use any measure to produce this sample. We can use, for example, for polynomials. If we are working with polynomial, we can use uniform measure. We get here square root of n squared, which give us n squared. Or we can use tensor product oxm measure. So we get square root of log of 3 over log of 2. So the idea is that we have an algorithm, we have a constructive algorithm with which we can produce points that have low Lebesgue constant. This is also possible using what is called Fekete point, except that Fekete points are hard to obtain because you need to maximize a determinant, and the maximization is over all the points. You need to maximize. You need to maximize a determinant to find x1 through xn all at once. But here, and you get a Lebesgue constant, which is n, actually, which is smaller than n. It's probably smaller than n. Here, we have a constructive algorithm using randomness that can produce a set of points that have also probably low Lebesgue constant. And let me finish now by, I think I have, if you give me 10 minutes, I'll finish by some numerical experiments. So in our numerical experiment on the paper, we just wanted to explore how these algorithms perform in a polynomial setting. So as I described before, we explored using polynomial multivariate polynomials indexed in lower sets. So let me remind some classical notation. So this LK are the Legendre polynomials, which form an orthonormal basis in this space. So the underlying measure is the uniform measure in -1, 1. And what I have here is what we call the generating function of the Legendre polynomials. So why do I introduce this function over here? So just so that I can so that our tensorize it and get these kind of expansions. And these expansion are typical representer of smooth function or of solution of the type of parametric PDE we have considered in previous paper, or many other authors have considered in their paper, just solution of parametric PDE that are highly smooth or have some anisotropic smoothness on the individual parameters, so they can using minimal condition on the parametric PDE in being studied, we can show that the solution R can be expanded in some Legendre basis or some Chebyshev basis or some other Jacobi polynomial basis with coefficients Ck, which are just multivariate power. This is almost like a multivariate power, except that there is a coefficient over here, but it's the same. So once we have this function over here, we will consider that we don't know the function. So what I do, I'll just let's say I have this coefficient, or I have upper estimate on this coefficient. So I truncate the set of indices. I'll just keep the indices associated with the largest coefficient, Ck. So here, lambda of n is the set of n multi-indices k with the largest Ck. Actually, these coefficients are non-increasing, are decreasing in the multivariate sense, let's say, and there's an algorithm so that we can find the corresponding indices. So these spaces, these set of indices lambda n, we can identify, and we can implement algorithms that find them once we have coefficients. So I'll just in our test we looked at this example over here in dimension d equal to 4, and we have a decay in y's, so we can get some anisotropy. Then we consider spaces of polynomial of dimension 128, and we consider the sample size equal to 2n. So the ratio I was showing in my theorems is let's say it's 2. So we truncate, we identify lambda n, and then we have compared sampling using i.i.d sampling or adaptive sampling, using Monte Carlo sampling, which in this case here is the uniform measure, or tensor product axon measure, or the Christoffel measure, related or associated with this, with the projection space, or algorithm 1 or algorithm 2. So what I show here is the condition number of the matrix gray mean matrix G obtained by each algorithm. And I think over 400 runs, we just look at the histograms of the, so this condition numbers can be seen as a random variable, and we'll look at the histogram of this random variable. So as you can see, for the uniform measure, we can go all the way up to 20,000 for the condition number. This situation is better with the arcsine measure because we get smaller number, but it's still centered around, let's say, 100. With Christoffel measure, we get even better result. We have condition number centered around 50. But with algorithm 1 and algorithm 2, we get even better results with condition numbers, moderate condition number in the 30s, 40s, or 20 on the 30s here. Although our algorithm, we have no guarantee on the largest eigenvalue of the gray mean matrix. So although we can actually, in this algorithm, we can force also the largest eigenvalue of the matrix to be low or moderate, but we didn't. But still, we get condition number of the gray mean matrix that is low and better than the Christoffel measure. I have also here for the same test the number of rejections. So what do I mean by the number of rejections? As I showed in the slide where I introduced the probability measure indexed by a matrix M, I showed you that the measure associated with some matrix M can be bounded by the measure, the Christoffel measure, up to some constants. And actually, we have used this formula. We can use this formula over here to so that when we need to sample from measure involved in a matrix, we use acceptance and rejection technique. So for algorithm 3 and algorithm 4, that's what we use in our numerical test. We just sample from the Christoffel and then decide to reject or accept. And what I'm showing you here is the average number of rejections over time. So since m is equal to 2n, so it's 256 over the course of these two algorithms. There is a price to pay. So the price to pay is the number of rejections and also of inversing matrices or solving linear system. And here I'm showing you the number of rejections. The number of rejections stay low up to the value n, let's say. And this we can show. This is there is a reason for this. I can, if you ask me this after, I can tell you why. And we have also, this is a different test. We have also, we have also compared the approximation using weighted least square with a sample obtained by Christoffel or a sample or samples obtained by algorithm 1 and algorithm 2. And we try to look in an interpolation regime, meaning m close to n. So I keep n equal to 128, but then m is range between this value and this value. And for every value, I I compute a weighted least square estimator for the three algorithms, and then compare the L2 error. Actually, we have access to the exact formula of the L2 error. If you look at the paper, this is something that can be done. So we have access to the L2 error, and I compare three algorithms. And I think every run is an average, is an empirical L2 norm over 400 runs. And as we can see, and as predicted by theory, the second algorithms perform well in an interpolation regime. And actually, it's outperformed all the other algorithms. The Christoffel is very bad in interpolation regime. And that's something, as I said, predictable, because for both of these algorithms, we are spending more effort in every to identify the next sample, and this effort involve rejection. As I showed, there is more rejection with the second algorithm than the first algorithm, and it also involved inversing matrices or solving linear systems. So sorry, I took 10 minutes.
Okay.
But I'll just, this is my last slide. This is just where I give you a conclusion as perspective of this preliminary work.